Assalamualaikum and hi everybody. I will explain chapter 7, Geometrical Optics. In Geometrical Optics, we have three subtopics: 7.1 Reflection at a spherical surface, 7.2 Refraction at a spherical surface, and 7.3 thin lenses. Let's start with the first subtopic. In first subtopic, you should be able to A. State radius of curvature R equal to 2F for spherical mirror. B. Sketch ray diagrams with a minimum of 2 rays to determine the characteristics of image formed by spherical mirrors. C. Use mirror equation 1 over F equal to 1 over U plus 1 over V for real object only. And D. Define and use magnification M equal to Hi over H naught equal to negative V over U respectively. We begin with reflection. Reflection of light is return of all or part of a beam of light when it encounters the boundary between two media. When you stand in front of plane mirror, you will see your image exactly like you. However, in this session, I will explain the reflection of light at a spherical mirror. Spherical mirror is a reflecting surface that is part of a sphere. There is two types of spherical mirror. First is convex mirror, also known as diverging mirror, and second one is concave mirror or converging mirror. To identify the types of mirror, we are looking at the reflecting surface. For convex mirror, the reflecting surface is curving outward. However, for concave mirror, the reflecting surface is curving inward. Now, look at terms of spherical mirror. Surface AB is aperture of the mirror. It is part of a sphere. Point C is center of curvature, which is in the center of the sphere of which curved mirror forms a part. Point P is pole. Pole is the center of reflecting surface of the spherical mirror. Principal axis. Principal axis is a straight line perpendicular to the surface and it is passing through point C and point P. The last one is radius of curvature. Radius of curvature is radius of an approximating circle passing through points on the curve. You measure radius of curvature from point C to point P. Next, we have focal point. Focal point is a focus point, and position of focal point is in the middle between point C and point P. Position of focal point for concave mirror and convex mirror is not the same. For concave mirror, focal point and center of curvature is in front of the mirror. However, for convex mirror, position of focal point and center of curvature is at the back of the mirror. Since focal point is focus point, therefore, all reflecting ray will converge at focal point for concave mirror but seem to diverge for convex mirror. Focal length is distance of focal point to point P. Since focal point for concave mirror is real, therefore focal length of the concave mirror always be positive. However, focal point for convex mirror is virtual. Then, focal length for the convex mirror is negative. Let's see the relationship between focal length and radius of curvature. Their relationship is radius of curvature is 2 times of focal length. Again, as I said, focal length for concave mirror is positive and focal length for convex mirror is negative. It does the same with radius of curvature. Means that for concave mirror, radius of curvature is positive. And for convex mirror, radius of curvature is negative. Next, we will do ray diagram. We draw ray diagram to locate the position of image as well as to determine its characteristic. Ray diagram has 3 methods. Let's start with first method. For first method, you draw incident ray parallel to principal axis. And after that, the ray will reflect and passes through point F for concave mirror but appear to come from the focal point for convex mirror. In second method, we draw incident ray passes through point F for concave mirror but directed toward point F for convex mirror. And after that, the ray will reflected parallel to the principal axis. In method number 3, the incident ray passes point C for concave mirror but directed toward point C for convex mirror. And then the ray reflected back along the same path. By combining 2 from any 3 methods, you will able to locate the position of image and state the characteristic of the image. Here we have example of ray diagram for concave mirror. If you put your object greater than point C, the image that you will get is real. Real means that the image form at the same side with object. The image is inverted. Diminish. Diminish means the image is smaller than object. And the image formed between point C and point F. If you put your object at point C, the image that you will get is real, inverted, same size, and the image also located at point C, same as object. Next, if you put the object between point C and point F, the image also real, inverted, magnify. Magnify means the image is bigger compared to the object and the position of the image is greater from point C. If you put the object at focal point, the image will form at infinity. Therefore, we don't know whether it is real or virtual. And the last one, if you put your image less than point F, the image will be virtual, means that it forms at the back of the mirror. And the image is upright, magnify. Next is convex mirror. Doesn't matter the position of the object, the image of convex mirror always be virtual, upright, diminish, and it form at the behind of the mirror. You can search for ray diagram simulation here. Either you click the link given or you scan by using QR code. Here we have spherical mirror equation. This equation is to show the relationship between focal length of spherical mirror with object distance and image distance, which is given by 1 over f equal to 1 over u plus 1 over v. F represents focal length of the mirror. U is object distance. And V is image distance. Here you need to be very careful with focal length, since focal length has sign convention, which is it is positive for concave mirror and negative for convex mirror. You also can substitute F with R over 2 into the equation of spherical mirror, and it turns 2 over R equal to 1 over U plus 1 over V. Next, we have magnification of spherical mirror. Magnification is the ratio between height of image to height of object, which is you can write the equation as M equal to HI over H naught equal to negative V over U. That is the meaning of value of magnification. If you get magnification is greater than 1, therefore the image is magnified. However, if you get M equal to 1, means that image is same size with the object. And if you get M less than 1, therefore the image is diminished. Besides, magnification also has sign convention. Magnification is positive if the image is upright. However, it is negative if the image is inverted. Here is the summary of sign convention for spherical mirrors equation. Object distance U is positive if it is located in front of the mirror, and we call that object as real. However, U is negative if you locate the object at the back of the mirror, and we call that object as virtual. Same with image distance. The image distance will be positive if it is located at the same side of the object, and we call that image as real, and image distance is negative if it is located at the opposite side with the object, and it is virtual image. And I repeat again, focal length for concave mirror is positive, however for convex mirror it is negative. That's all for subtopic 7.1. Next, I will explain for subtopic 7.2. Let's go for second subtopic, refraction at a spherical surface. In this subtopic, you should be able to use equation N1 over U plus N2 over V equal to N2 minus N1 over R for spherical surface. In this figure, a spherical surface with radius R is dividing two different media. Let's say medium at the left is air and at the right is glass. This media have its own refractive index named N1 for medium air and N2 for medium glass. An object is placed at point O in medium air and image is formed at point I in medium glass. Incident ray OB from object is making angle I from normal and refracted to refracted ray BI, making an angle theta from normal. Normal is line BC and point C is center of curvature for spherical surface. You can relate the refractive index, object distance, image distance, and radius of curvature for spherical surface by using equation of spherical surface, given by n1 over u plus n2 over v equal to n2 minus n1 over r. As usual, u is object distance, v is image distance, n1 is refractive index of medium 1. To identify the medium 1 is medium with incident ray. N2 is refractive index of medium 2, which is the medium with refracted ray. And if the surface that dividing between two different media is flat, therefore radius of curvature is equal to infinity. And if you substitute r equal to infinity into equation of spherical surface, it will turn that n1 over u plus n2 over v equal to 0. Here is the sign convention for refraction at a spherical surface. The object distance u is positive. It is located in front of the refracting surface, and we say the object is real. However, u is negative if it is located at the back of the refracting surface. Image distance is real, or you get positive sign if it is located opposite side of the object. However, v is negative if it is located at the same side of the object. Radius of curvature is positive for convex surface, means that the surface is curving outward. However, radius of curvature for concave surface is negative, means that the surface is curving inward. That's all for subtopic 7.2. Let's return to our initial page. We had reached final subtopic 7.3, thin lenses. In this subtopic, you should be able to A. Sketch ray diagrams with a minimum of 2 rays to determine the characteristics of image formed by concave and convex lenses. B. Use thin lens equation 1 over f equal to 1 over u plus 1 over v for real object only. C. State and use lens maker's equation 1 over f equal to refractive index of material divided by refractive index of medium minus 1 times 1 over R1 minus 1 over R2. And D. Define and use magnification M equal to HI over H naught equal to negative V over U respectively. Thin lenses is defined as a transparent material with two spherical refracting surfaces whose thickness is thin compared to the radii of curvature of the two refracting surfaces. We have two categories of thin lenses. First is convex or converging lens, and another one is concave or diverging lens. Each of category, it has three types of lens. Either biconvex lens or biconcave lens. Plano, either plano-convex or plano-concave lens. And meniscus, either convex meniscus or concave meniscus. This is terminology of lens. We have principal axis shown by the red dotted line, which is line that passes through center of curvature of two surfaces. Next is optical center, point P. When a ray passes through this point, it will continue in straight line. Then we have focal point F. When parallel rays reach the lenses, ray will reflect. Either it converge if convex lens or diverge if concave lens. Focal length is distance between point P and point F. Let's see how to draw ray diagram for convex lens. Like mirror, we have three methods to draw ray diagram. Method number 1, incident ray that passes through optical center, point P, will continue in straight line. Method number 2, incident ray that enter parallel to the principal axis will refract toward focal point. And method number 3, incident ray that passes through focal point in front of the lens will refract parallel to the principal axis. You need to combine any two from three methods to locate the image. Here we have ray diagram for convex lens with different position of object. Number 1, if the position of object is greater than 2 times of focal length, the image that you will get is formed between point F and 2F, and it formed at the back of the lens. Means that opposite side with the object. Therefore, the image is called as real, and it is inverted, and it diminish. Next, if you put your object at 2F, the image that you will get, it form at point 2F, and it form at the back of the lens or at another side from the object. Therefore, the image will be real, inverted, and same size. Then, if you put your object in between focal length and 2 times of focal length, the image that you will get form at the distance greater than 2F, and it located at the back of the lens. Therefore, the image is real, inverted, and magnified. If you put your object at point F, therefore, the image that you will get, it form at infinity. And we say the image either real or virtual. And if you locate the object less than focal length, the image that you will get, it form in front of the lens or at the same side of the object. Therefore, the image will be virtual, and it is upright, and it magnify. And the last one, if the object is at infinity or at the longer distance, the image that will form at point F, and it is real, inverted, diminish. You can search for ray diagram simulation here. Either you click the link given or you scan the QR code. Now we have image formed by a concave lens. For concave lens, doesn't matter where you put your object, the image will be always virtual, upright, diminished, and of course it form in front of the lens or it form at the same side with the object. Next, we have thin lens equation. Look at the figure given. You have a lens and you put your object in front of the lens. You measure the distance between the object and the lens and you put it as U. The image is formed at the back of the lens and you measure the position of the image to the lens and you put it as V. The relationship between object distance, image distance, and focal length is given by the equation 1 over f equal to 1 over u plus 1 over v. And here, you must be very careful with the sign convention of focal length. Focal length is positive for convex lens and it is negative for concave lens. This is the summary for sign convention for thin lenses. The object distance u is positive if you put your object in front of the lens. And we call that object as sphere. However, if the object distance is negative, it means that the object is at the back of the lens. And we call the object as virtual. For image distance, it is positive if it forms at the back of the lens or it forms at the opposite side from the object. And we call that image as real. However, if it forms in front of the lens or same side with the object, therefore, you put negative sign at V and the image is virtual. Focal length for convex lens is positive. However, focal length for concave lens is negative. For magnification, it is positive if the image is upright. And it is negative if the image is inverted. Now we have lens maker equation. The equation is 1 over f equal to n material divided by n medium minus 1 times 1 over r1 minus 1 over r2, where n material refer to refractive index of the lens, n medium refer to refractive index of the medium surrounding the lens, r1 is radius of curvature for first surface, r2 is radius of curvature of the second surface. If you put the lens in air, therefore refractive index of the medium is equal to 1. And you substitute it into the lens maker equation, it will turn 1 over f equal to n material minus 1 times 1 over r1 minus 1 over r2. Radius of curvature has sign convention. R is positive if the surface is convex surface, which is the surface is curving outward. However, R is negative if the surface is concave surface, where the surface is curving inward. Let's see how to decide which surface become first surface and second surface. Here it shows the direction of the light is to the right. Therefore, the ray encounters surface at the left first and then it encounters surface at the right. It makes left surface is the first surface and right surface as second surface. To determine the sign convention of R, we are looking at the surface where the ray is encountered. I take biconvex lens. The ray encountered first surface and the surface is convex surface or it curving outward. Therefore, it will be positive R1. Next, the ray encounters second surface and the surface is concave surface or it curving inward. Therefore, R2 will become negative. Let's take another example. Let's say I take plano concave. The ray encounter the first surface and the surface is curving inward. It is concave surface. Therefore, R1 will be negative. And the second surface is flat. Since it is flat, it will become infinity. This is how you determine the R1 and R2 and their sign convention. Last is magnification. Magnification is ratio between height of image and height of object, where you can write it into m equal to hi over h naught. At the same time, hi over h naught equal to negative v over u. Therefore, you can write magnification equal to negative v over u. Or you can simplify, write down m equal to hi over h naught equal to negative v over u. Magnification also has sign convention. If you get positive m, it shows that the image is upright. However, if you get negative m, therefore the image is inverted. Value of magnification also give great rule. If you get magnification is greater than 1, it shows the image is magnified. If m is equal to 1, therefore the size of image is equal to the size of object. And if you get m less than 1, therefore the image is smaller than the object. That's all for Chapter 7, Geometrical Optics. Thank you for your attention.